Okay, we're going to go ahead and take a look at this one right here. So we have an orifice discharging to the atmosphere, and there's a drawing of a tank. Let's go ahead and look at the drawing of that tank. So the tank is pictured here. And the question is, what is the velocity of the discharge coming out of that tank? Now, what we have is water, and this is not exactly to scale. You could see this is 25 millimeters in diameter, which is roughly an inch. And this is 20 meters deep as a tank. So we're going to figure out what is the velocity here. Well, this problem really relies on you thinking about the difference in the water that is inside the tank here and the water that is being discharged here. So it's being discharged to the atmosphere, and obviously if we consider what it's like to be a water molecule right here, we know that this water molecule is going to be under a particular pressure, and this shows that that spot is 20 meters under the water. So what is the pressure right there? Well, we know the pressure is going to be whatever the atmospheric pressure is plus the pressure that is applied by being 20 meters deep into this tank. And out here, what we know is that we have just the atmospheric pressure. So what we can do here is use the Bernoulli equation to state that the pressure, let's put points, let's actually name these points. We'll call this point 1, we'll call this point 2. And the pressure at point 1 plus the density over 2 times velocity 1 squared is equal to the pressure at point 2 plus density at point 2 times density over 2, velocity at point 2 squared. And this is the Bernoulli relationship. And of course it doesn't have a gravitational term, because this is just a horizontal transfer of fluid here to out here. There's no change in gravitational potential energy. So okay, so let's rewrite some of this. We know that P1 can be rewritten as the atmospheric pressure plus the pressure that you experience as you drop down into this water so that you get down to point 1. And so that would be equal to rho times G times H, which we know in this case is 20 meters. Now, the velocity here is going to be whatever the velocity is right inside this point as you discharge this thing. So this velocity inside here is, we could write this really as not moving at all. So this is going to be essentially 0. So this becomes equal to P2, which we will write now, P2 as the atmospheric pressure. And there's no other pressure term here because we're simply out in the atmosphere. And the other term here is this term, which is the dynamic pressure. It's equal to rho over 2 times V2 squared. This is actually the pressure that we're looking for, this V2 value. So I can see that the pressure from the atmosphere drops out, and I'm left with this equation that I can see here that density drops out as well. So I'm left with this equation, G times H times 2 is equal to V2 squared, or V2 is equal to the square root of 2 times G times H. Obviously it's not going to be plus or minus the square root of that, but the square root of that. So solving this should give us the velocity that this jet is experiencing as it exits this orifice is the square root of 2 times 9.8 meters per second squared times 20 meters. And this is, okay, I'm just kind of ballparking this just to kind of see how big it's going to be. So this is like 2 times 10, 20 times 20 is 400. So it's going to be on the order of 20 meters per second. So this term right here, I'm doing this in my head, is roughly 20 times 20 is 400 meters squared per second squared, roughly. So it's about going to be roughly this value, and I can use a calculator to get a closer number. Why don't I do that? Oops, got to turn it on. 19.8 meters per second is the velocity if we cared about 3 significant figures. In this problem, we only have one significant figure, which is the, it says it's 20 meters, so we only have one significant figure. So this, a very legitimate answer here would be 20 meters per second as the initial velocity.